Good morning. I would like to begin by thanking the organizing committee for the invitation to give this talk and apologizing for not being able to attend in person. So let's begin. The word paradigm is commonly used in epistemology of science, especially since Thomas Kuhn gave it its current meaning in the 1960s and 1970s, starting with the publication of his seminal book on the structures of scientific revolutions in 1962. However, it is not a simple term to define. For my part, I would say that a paradigm is an idea accepted so absolutely that it does not occur to us that it can be otherwise. In other words, it would be as if our brain is wired in such a way that it's nearly impossible to think outside those limits. Obviously, there are paradigms in all order of lives, but we will restrict ourselves to their application to the world of physics. There are always mad people, lunatics, or visionaries like Galileo willing to question our paradigms, but the paradigm works like a boxer. Although the other way around, the more punches he receives and the more he resists, the stronger and healthier he becomes. Otherwise, it would not be possible to explain how the Ptolemaic geocentric model resisted for 2 millennia. Of course, paradigms come in different sizes. For example, a very strong paradigm would be to say that the causes precedes their effects. Continuing with our boxing metaphor, this paradigm would be of a heavyweight division. If someone wants to convince us that it is not valid, he or she would be questioning our very understanding of reality. There are other paradigms that militate in the welterweight division. For example, that in quantum physics, it has no meaning to assign a trajectory to a particle, even though for more than a decade there has been experiments that contradict this statement. Very few colleagues are willing to accept this falsehood, and even those who already do so reluctantly. Finally, there are lightweight paradigms. For example, in our area of research, we assume without question that cross-sections are all that there is to be measured and calculated, when in reality, cross-sections are only the diagonal terms of a huge matrix. Outside the diagonal where cross-sections live, there are complex quantities that can be measured and are meaningful and important, but of which, in the worst case, we ignore their existence, and at best, we do not pay attention to them. In very few opportunities, a paradigm is overtaken by the evidence against it, and then, as Thomas Kuhn taught us, science becomes extremely interesting. When a boxer falls for knockout, an era of normal science ends and a scientific revolution begins. This is called a paradigm shift. Here, I would like to review some few paradigmatic assumptions of atomic collision physics. Of course, I am not trumpeting a revolution, as these are flyweight and amateur category paradigms, but I think it's good to review them to at least be aware of their existence and wary of their implications. Let's start by going to the roots of these ideas. That is, like in a journey in the time tunnel, going back to the moment in the history of atomic physics almost 70 years ago, when one of these paradigms was first phrased by this physicist who possibly is not familiar to most of us. His name was Giancarlo Wick. He was one of those morally healthy physicists of the 20th century, and as one of his friends Viktor Weisskopf used to say, lived a happy life in a dreadful time. He was born and studied in Torino. During his youth and his entire life, he was actively against all forms of totalitarianism. Here we see him posing with some other renowned anti-fascists. He received his doctorate in 1930 and later spent time in Göttingen and Leipzig. He became good friends with Werner Heisenberg, with whom he shared a taste for classical music, mountaineering, and table tennis. In 1932 he joined the famous group of Enrico Fermi in Rome, I ragazzi di via Panisperna, that is, the boys of Panisperna Street. Here we see him, Fermi, and Amaldi spending some time in Ostia in 1836. His memoirs of I ragazzi di via Panisperna were published in September last year. It is a very interesting and enjoyable book, also in Italian, of course. In 1846, he followed Fermi to the United States, first to the University of Notre Dame and then to Berkeley. By 1949, anti-communist pressure has escalated, and all Berkeley appointees were required to disavow the Communist Party. Giancarlo was as far of being a communist as he was of being a fascist, and declined to take the oath. Due to this decision, Ernst Lawrence expelled him from Berkeley with the following outburst: "Get the hell out of the rat lab." Luckily, he quickly found work at the Carnegie Institute of Technology in Pittsburgh. In his old age, he returned to his hometown, where he died at the age of 82. Today, he is recognized for his work on quantum field theory, such as Wick's theorem of 1950 or Wick's rotation of 1954. For research like this is that in 1968 he was the first recipient of the prize named after Ettore Majorana, his ill-fated colleague and friend of his years at the Institute of Rome. Well, if I can spend these minutes remembering Giancarlo Wick, it is precisely because 70 years ago he proposed an idea that has become one of the paradigms of collision theory. Obviously, it is a minor but very important result for our area of research, and in all fairness, it is called Wick's argument. While Wick raised this argument in 1852, he did not write or publish it. To find it, we must go to a note added in the Galli proof of a 1953 paper by Jackson and Schiff. There, the authors claim that Wick pointed out to them that in an electron capture collision the internuclear interaction would give a negligible contribution, and that it can therefore be eliminated from the Hamiltonian. That in 1950s someone came to tell that a term could be removed, reducing the effort and calculation time, was happy and important news, for the simple reason that there were no computers and everything had to be done analytically at best and by hand at worst. Of course, if this argument was good for electron capture, it was also good in virtually any other case, such as excitation or ionization, given the provision that the projectile should have to be a heavy particle. And the latter is very important, since Wick warns us that this approximation is valid in a range of the order of the ratio between the mass of the electron and the mass of the ions involved, and so we continued from then on. But Wick's argument does not end there. He goes on to propose that we can consider the nuclei to be infinitely heavy and configure the problem as an impact parameter calculation. And we do follow this advice, we really do. A vast majority of the theories we use to analyze heavy particle impact collisions assume that the projectile follows a classical rectilinear and uniform trajectory. It is fair to say that this second, even stronger approximation was far from being new, since it had already been proposed more than 2 decades earlier, in 1830, by Cohen-Brickman and Hans Kramer, as we can see in this figure extracted from their original paper. And finally, going back to Wick's argument, he says that the internuclear interaction can be removed from the Hamiltonian by an appropriate canonical transformation. And when we talk about the Hamiltonian, we are basically talking about a modification of the quantum state, solution of the general-Schrödinger equation, in the transition matrix. Thus, we have these 3 approximations, which are at the basis of a vast majority of our current calculations, and which we use almost without thinking about them, much less questioning them. And everything is well if what we are doing is calculating total cross-sections. We can even calculate ionization cross-sections differential in the energy and angle of the emitted electron, in what we call electron spectroscopy, and everything will be okay. And this was all there was to measure, and therefore to calculate, for many, many years, until the experimentalists tried to ruin the life of us poor theorists with the new technical skills which allowed them to measure, for example, the deflection angle of the projectile. Well, if the projectile is deflected, one would think that there is no way to maintain Wick's argument. How can we possibly maintain the hypothesis that the projectile follows a rectilinear and uniform trajectory if we want to study its deflection? It wouldn't seem to make no sense, wouldn't it? And here, the epistemology of Imre Lakatos enters the scene. In 1870, he explained that each theory has a hard core of assumptions that cannot be abandoned or altered without abandoning the theory altogether. Thus, when something appears that threatens the hard core, a patch is attached to the theory. These so-called auxiliary hypotheses are considered expendable and may be altered or abandoned as empirical evidence requires in order to protect the hard core. And this is precisely what happened to the theories based on Wick's argument. Of course, measurements including a projectile deflection were considered as red flags. But if that angle remained at a reasonably small values, that is, in the order of the ratio between the masses of the electron and the projectile, everything should be fine. This defense of the hard core of Wick's argument required the inclusion of several auxiliary hypotheses. The most common was to continue using the model as it was, but associating a classical deflection angle to each impact parameter. Let's see how it works in a specific case. So let us study the double scattering mechanism in electron capture collisions proposed by Lewellyn-Hillett-Thomas in 1927. This is a diagram of this mechanism that I took from the book of Blansden and McDowell. Let's mention that being 30 years old, this book, that every self-respecting theorist has surely read, can already be considered a classic. Since Thomas' angle is of the order of ratio of masses, everything should be okay with the theories based on Wick's argument. Well, maybe not so. In this figure that I also took from this book, none of the theories work very well, even on a logarithmic scale. In these last 3 decades, there have been many advances, and the agreement has certainly improved. But as we increase the scattering angle, the comfort zone of Wick's argument fades away as the gradient in violet. So what would happen if we took this scattering angle to the limit and beyond? But first, it is important to clarify something related to the theories that we have just shown in the previous graph, which are commonly known as distorted wave. Their conceptual basis can be traced back to an equation known as the formula of the two potentials, first introduced in 1952 by Kenneth Watson, who, by the way, turned 101 on September 7. The idea is to modify the transition matrix to include distorted waves that would represent more accurately the initial or final scattering states, as seen in this equation taken precisely from this article. This expression was rediscovered a few months later in an article published by Murray Gell-Mann, who in 1969 would receive the Nobel Prize in Physics, and by Marvin Leonard Murph Goldberger, a doctoral student of Enrico Fermi. It should be noted that in a footnote, Gell-Mann and Goldberger accepted the primacy of Kenneth Watson regarding this discovery. Without citing either of these two previous papers, 1 decade later, 2 other articles appeared, sent to publish with a difference of just 3 months. There, the authors propose a simple and practical application of the formula of the two potentials in the presence of Coulomb interactions. Basically, it was about distorting the wave functions with the same factors that distort plane waves in the presence of Coulomb interactions. Due to this particularity, Cheshire, who at the time was a student of Bransden in Glasgow, named this theory as Continuum Distorted Wave Approximation, or CDW. Beyond the obvious difference that in one case this approach was used to study an excitation collision and in the other a charge transfer process, Cheshire's approach incorporated an additional approximation. Guess which? Yes, the Wick's argument, in particular the impact parameter approximation. In this way, the CDW theory came to include an additional approximation that does not make it to its essence. And today, when we use the acronym CDW, in general, though not always, we are tacitly presupposing the existence of that combination of the distorted wave and an impact parameter approximation. This is as far as I will go with this historical and critical review. I just want to add that these two articles acted as a watershed, with some colleagues applying Cheshire's approach, including the semi-classical Wick's argument, and the others following the purely quantum proposal of the colleagues from the Lebedev Institute. The timeline of the semi-classical CDW approximation is easy to trace through its more than 300 citations. However, that of the purely quantum theory is more difficult, since, as far as I know, the Soviet physics GETP article is not indexed. So, focusing again on the impact parameter approximation, under what conditions can it fail? Well, clearly, whenever the mass of one particle is not much smaller than those of the other two. This is clearly the case when the projectile is an electron or a positron. In addition, in this case, we must go a step further and fully incorporate the distortion due to the Coulomb interaction between the projectile and the nucleus of the target, which was previously included only as a phase according to Wick's argument. Here I show you a calculation, more than 2 decades old, for the ionization of hydrogen molecule by positron impact, compared with experimental results from the group of Nella Laricchia in London. Note that we are not using a logarithmic scale, but a linear one, so the agreement between the experimental and theoretical results when Wick's arguments are not considered is extremely good. The previous data corresponded to the emission of the electron and positron in the forward direction. When we remove this condition, the situation becomes very interesting, since even if we maintain a coplanar condition, that is, that the electron and the positron move in the same plane, quantum vortices appear as exact and isolated zeros of the transition matrix. When we look at this graph, not plane by plane but in a 3D format, we notice that the isolated zeros that we have just seen correspond to a vortex line. And if we complete the graph, we find that this line is just a fragment of a very complex vortex ring. Finally, to fully understand the topology of this fascinating quantum structure, we are beginning to trace the vortex in the full multidimensional space of the transition matrix element. So, we are freeing ourselves from any restrictive geometry. This is a work in progress, but I can show you some first results. Here we see the vortex rings plotted as a function of the three components of the electron impulse, for different values of the exit angle of the positron. What I have shown you is still theoretical speculation. Thus, the question arises whether it will be possible to experimentally confirm the existence of vortices in positron impact ionization collisions. Obviously, it is not easy to measure E0, especially in experiments as demanding as those involving positrons. But some time ago, we proposed a crucial experiment where the proximity of a vortex alters the electron capture to the continuum cusp. The vortex produces a reversal of the cusp symmetry that, for an energy of 50 eV, occurs just as the positron is deflected to 25.5 degrees, and this would be relatively easy to measure. And to make things easier, another option would be to measure the yield of the ionization cross-section in a given energy range as a function of the emission angle, which should show a very pronounced minimum. I have shown you these results to exemplify how rich and interesting physics can be if we go beyond the constraints of Wick's argument. But what happens when the projectile is an ion? Does it make sense to abandon Wick's argument? Well, the answer is whether, as in the previous case, we are venturing beyond its limits. Let me show you these experimental results obtained more than 2 decades ago by our colleagues from Debrecen. They correspond to the ionization of argon by the impact of 75 keV protons. Here the projectile and the electron end at the same angle at 3.7, 5, 6.8 and 8.1 degrees. In the lower part of the second figure, we also see the case where the electron is measured in the forward direction and the proton at 6.8 degrees. The performance of the continuum distorted wave model with the impact parameter approximation would be even worse than shown here. But it was not so, since the authors used a broken line approximation in which the straight projectile trajectory was replaced by its two classical asymptotes. This provision improved the agreement, but clearly was not enough. There has also been an attempt to use a hyperbolic trajectory, but the results were not better, and as far as I know, they were never published. And these are the results obtained by using a CDW model which does not employ any of the approximations suggested by Wick's argument. This model not only reproduced very well the form, but also the scale of the experimental data, and without including any artifice. The obvious conclusion should be that when dealing with the projectile scattering angles, Wick's argument should be ruled out, even for deflection at a small fraction of a milliradian. But as Kuhn and Lakat have shown us, this is hardly the case. Here we see a very recent comparison of the standard CDW model with some experimental results by our colleagues from Missouri Rolla for the ionization of helium by the impact of protons of 75 GeV. We show the fully differential cross-section as a function of the electron energy when the electron is emitted in the forward direction and the proton at a very small angle of 0.5 milliradians. The performance of the CDW model with Wick's approximations, represented by the green and blue lines, is very poor. The red line, which does not do very well either, is another type of theory. We were starting the calculations to compare with these results when we stumbled upon something unexpected. The experimental data seemed to indicate the presence of a minimum near 8 eV, and when we looked in more detail, we discovered that it was something more. It was an exact zero. To be completely sure, in this figure we show you where the real and imaginary parts of the transition matrix are cancelled, and effectively these two lines cross at an energy of 8 eV and an angle of 0.47 milliradians. This result was a real shock. We were not expecting to find a quantum vortex in the case of proton impact, but here it is. Obviously, this discovery diverted us from the initial plan and put us on the laborious path of tracking this amazing structure. We hope to have more to tell in the near future. And that's it. In this presentation, we have tried to review, not as a criticism, but as a trigger for reflection, the paradigm of Wick's argument that we incorporate into our theories, sometimes knowingly and sometimes without realizing it. So we can abandon Wick's argument if circumstances call for it, but let's not forget to correctly take into account the distortions due to long-range interactions. Monsieur Coulomb and the precision of the theories will thank us. Thank you very much for your attention.